MC² STEM High School.
Hi, I'm Andres Howard from Lincoln West School of Science and Health.
Hi, I'm Metropolitan and I teach at Cleveland School of the Arts.
And we want to welcome you back to CMSD on WUAB.
Today, we are going to focus on cause and effect. We're going to look at cause and effect in ELA so that we can comprehend them and apply them in the sciences.
Cause and effect is a very relevant concept in science. It's very significant in science, and you're going to see very cool experiments done by us today. So enjoy.
You've probably seen this experiment before, but stay tuned. Later on, we'll find out why it works. Ready?
Hello, everyone. This is Andres Howard from Lincoln West School of Science and Health. Today, we're back and we're going to focus on cause and effect. Everybody say yay. I'm so excited. Cause and effect is, so we're going to learn the foundational skills of it today first. And then later on, you're going to apply it into a science experiment. Oh, so exciting. I know. Now, when you think about cause and effect, you're like, oh, I know what that is. You find the root issue, then you find out why it happened. Correct. But cause and effect can also be applied in different formats, different situations, different scenarios. And today, with the slides that I'm going to preview with you, we're going to look at how cause and effect is applied in different scenarios, schemes, situations. Because every day, everything that you do, every decision that you make is affected with cause and effect. So, get ready. So we're going to first start off with, what do you know about cause and effect? What are some general things that we know? So yes, we know that a cause is when something happens. So we've established that something has happened. What else do we know? What else is a cause? So yes, a cause could be like, I am on a mission. I'm fundraising money and I'm a philanthropist, right? So you have a cause that you're fundraising money for. We're not talking about that kind of cause and effect. We're talking about the cause where a situation has occurred and it happens to be a result, something has resulted from it. That's the type of cause and effect that we are focusing on today. So we're first going to start off with, what is a cause? What is cause? When searching for the cause, you are looking for the root of the issue. What is the root? Where has it derived from? Where does it begin? Where does it start? Then you're going to think to yourself, and you're going to ask again, where did the issue derive from? Then you're going to define what that problem is. Anybody know what I mean by define what that problem is? So there could be many causes, tons and tons and tons of them. But you want the cause to be directly attached to the effect. Not something like, maybe just a little bit it could be direct affected. No. What is a direct link? So what do you have to, so you first have to define that problem, so then you can find that direct link. Because there could be many causes, but is it really attached to the effect is our question. And then next you're going to begin to think about the effects that root cause and the root cause is having. So first we're going to start searching. What is the root of our issue? Remember, root of the issue is your cause. When we think of root of issue, we think of our cause. Where does it derive from? Where's the source? And define what that problem is, and then we're going to move on to find the direct link to it has on the effects. What is effects? Now, effects are a direct result from a cause or root issue. So it is directly linked. It is no gray area. It's either black or white. It either is or it isn't. Okay? Effects are the consequences of an action or a decision. So it is a consequence. It is direct consequence of what happened with that issue. So your cause is your issue, and your effect is the result and the consequence of that issue. So you're going to ask yourself, does my identified root cause have this effect or consequence? So when you're thinking about your effect, does your identified root cause have this effect or consequence? Is it directly linked? If it is, you can then move on and begin to search for solutions. So we have a few examples of cause and effect. So we kind of figured out what the definition is. Again, a cause is your direct source, like with the direct root of the issue, and the effect is linked. So that is a consequence and the result of that cause, of that issue, of that source, okay? So I have a few examples, and my first one is air pollution. These are topics that are actually happening right now, very controversial topics. So the topic is air pollution. Our cause, so our direct issue. Now there are many causes of air pollution, so I want you to think about how my effects and my causes are similar, or very much linked. So you have your topic is air pollution, then your cause is vehicle emissions. So the fumes that are coming out of your vehicle would be the cause. And what is it doing to the air? It contributes to the depletion of the ozone layer. Pay close attention to the words that I'm using. Contributes. I am not saying like this is the sole purpose of why we have issues with pollution in the air, but it is a contributing factor. So our cause is vehicle emissions. Our effects are it contributes to the depletion of the ozone layer. And our solution, so when we are thinking about cause and effects, how can we solve these issues? Our solutions would be to drive less, purchase fuel-efficient vehicles. So if you are into cars, I would suggest maybe a Tesla. I'm really into Teslas right now. A Tesla, because it is an electric car. Or you have a newer car that is less on gas and has better fuel mileage. Or fuel efficient. That would be direct solution to this. Example of cause and effect. Now this is to my high school students, because you are writing a lot, and my future seniors, my rising seniors, and my seniors who are going off class of 2020. This is huge. Plagiarism. So this is an example of cause and effect. So our topic: how plagiarism may affect education and relationships in class. Your cause, plagiarism. We all know what plagiarism, right? What it is. For those of you who do not know, plagiarism is when you take a piece of work and you basically copy and paste. You copy and paste, you copy and paste. You do not correctly cite the material, nor do you provide evidence to support your argument. So, one, if you are taking evidence from a text, you have to, first properly cite it. And then two, you have to actually prove it. Explain it. That's how you avoid plagiarism. That's just like a key. If you copy and paste it, boom, put it there. You have not, you didn't give the author credit. You've stolen a piece of work and you have copied. You have not done the assignment. So that is what plagiarism is. So the cause is you copy and pasted work. You have not cited it. You have not explained it. You have not supported it. It is just there. And me as the English teacher, I am wondering what is going on. I'm going to assume that you have plagiarized. The effects you are going to have is a failing grade and mistrust between instructor and student. Normally teachers are not going to trust you anymore. I'm going to be a little bit more cautious, give you a lot more assistance, and you're probably not going to pass, especially if you have plagiarized last minute and the assignment was due. Now, we can avoid all of these things with our solutions. So our solution is to seek help and pay attention in class. The first one is crucial: seek help. If you are not understanding something, seek help. To not understand something is a direct result in doing something wrong. That is an example of cause and effect. Another example is bullying in schools. So we have a topic. Our topic is bullying in schools. Our cause: no adequate self-control. So if you are a bully, you do not have adequate self-control, and you intend to provide harm to another person. That is a root cause. That is why people bully. The effects of bullying. So this is what is going to happen to the person that you have mistreated. they're going to have poor academic performance and they have low self-esteem. So you have made this individual feel really, really bad about themselves, and they're not performing at their highest ability. Solutions: speak with a guidance counselor and or seek mediation at school. So you need to speak with a guidance counselor or you need to seek a mediation. We have a lot of resources to help you if needed. This is just an overview of cause and effect words in English. So take a moment to just briefly look over these because this is going to help you to understand our next two science experiments we are about to embark on.
Hello, this is Mrs. Cherubu and I teach chemistry at Cleveland School of the Arts, and I'm really glad to be back. Today I'm going to show you a very cool magic trick. So what I have in this container is a purple blue liquid, which I call as magic liquid, and I'm going to try changing the color of this liquid into different colors. Alright, so let's go ahead with changing colors. So the first color I want is red, so I'm going to do my cool magic trick, and then I'm going to pour this liquid and pray that it changes its color into red. And yes, it did. Alright. The next color, as you notice, it's really deep red. The next color I want is magenta or deep pink. So let me go ahead and do my magic trick and pour this liquid. Alright, so I did not get pink. I got purple color. But if you look carefully and you wait a little longer, you do see the color changing into magenta color. Okay, so it is magenta color. Next, I would like to see maybe purple. So let's try this time if I can get it right. So let me do my magic first. Alright, I'm going to pour this liquid. Yes, I was able to create purple. Wonderful. I'm getting more confident now. Next, I'm going to create maybe deep green. All right, let's try deep green or forest green color. Wow, I got deep green or forest green color. Wonderful. Let's try a different color this time. Maybe this time I would like to see yellow. So I'm going to go ahead and pour this liquid and try to get yellow color. Ooh, this is bright yellow color. That's wonderful. Next, I'm going to go ahead and get maybe red again or a different shade of red. Let me try. Alright, so I have red again. It's a slightly different shade of red. Well, I hope you enjoyed the full range of colors that I produce. And, I hope you're also wondering, how am I able to make all these colors? Well, this is really simple. Even you can do this trick. What you actually saw is a phenomenon of action and reaction come life. In science, action and reaction is a very important concept. It's a very relevant concept. So what you actually saw was a pH indicator. So what I had as a magic liquid was in fact a pH indicator, changing colors when mixed with acids and bases. So my action of mixing two substances or chemicals resulted in the reaction of changing color. So before I teach you how to make this pH indicator or your own magic liquid, let's look closely the concept of pH, as we always do in science. So pH could be elaborated as power of hydrogen ions or power of hydronium ions. Now, what do we understand by hydrogen ions or hydronium ions? To understand that, let's examine water more closely. So I have this cute little model of water which I made from marshmallows. The blue representing oxygen atom, the pink hearts representing two hydrogen atoms, and then I have yellow which are representing shared pair of electrons. So this is one shared pair of electron, the other yellow marshmallow represents another shared pair of electron. So there is no secret that the formula of water is H2O. That means it's made of one oxygen and two hydrogen atoms that are covalently bonded. That means where there is sharing of electron between them. So technically, water should not make any ions because ions can only be formed only if the atoms lose or gain electrons. Here, water is not losing electrons. The atoms are not losing electrons. They're simply sharing electrons. Now, why in the world water is still able to make ions even though in a very meager quantity? So that's because water is a polar molecule. And to understand why it's a polar molecule, let's examine the molecule more closely. As you can see, oxygen and hydrogen, they share electrons, right? And so when you share electrons, the electrons should be, ideally, the electrons should be right in the middle. But in reality, what happens is this shared pair of electron, instead of being right in the middle, it gets pulled by oxygen, this blue oxygen, more towards itself. So it's not like the oxygen completely has it, but it gets pulled more towards oxygen, even though they are still sharing. And therefore, what happens is oxygen develops a partial negative charge, whereas hydrogen, on the other hand, becomes partially positive. And that happens for both the bonds. Now, this happens because oxygen is highly electronegative. That means it attracts the shared pair of electrons more strongly. And therefore, there is unequal sharing of electron, as you can see. Because of this unequal sharing of electron, we have a permanent partial negative charge on oxygen and permanent positive pole towards hydrogen. And therefore, water is a polar molecule because it has a permanent separation of charges. And this is also called as a permanent dipole. Now, this is a very important fact about water, that it's a polar molecule. Because it's a polar molecule, it behaves in a peculiar way. There are a lot of properties that water has because of that fact. So, if we were to examine polar molecules and non-polar molecules, so on the other hand, non-polar molecules are the ones where there is no unequal sharing of electrons, right? The electrons are shared equally. That means the shared pair of electrons should be right in the middle, right? And therefore, there is no separation of charges. So non-polar molecules and polar molecules, they behave very differently. Because water has partial positive and partial negative poles. And therefore, if I try to bring any statically charged object close to water, then the molecule should get attracted to it. So what I decided to do is I decided to generate some static charge on the balloon by rubbing it against my woolen sweater. And then I'm going to test out two liquids. One of the liquid obviously is water, and the other liquid is xylene. So xylene is something that's used as a solvent of paints. It's a very good solvent that can dissolve non-polar molecules. So it is a non-polar molecule that can dissolve other non-polar molecules. And this is the only liquid I could find around in the house that I could test out. So let's make our observations. So I'm going to create a fine stream of water with my other hand without touching the balloon, because as soon as you touch the balloon, you dissipate all the charge, all the static charge that you generated on it. So make sure you don't do that. Your hand should be dry. And so I'm going to try creating a static charge. I'm going to make a stream of water and then bring my balloon close to it. I hope you made that observation. As I bring the balloon close to it, it bends in the direction of the balloon. Again, as you can see, it's bending in the direction of the balloon. And as you can see, this part of my table is all wet because the water was bending in the direction of the balloon. Right, so here I have another balloon which has also been statically charged, and I'm going to make a stream of xylene and bring this balloon close to it to see if the stream bends. So as you can see, I don't see any difference. There is no bending that I observed. I'm going to show you again. And as you can see, it's not affecting the balloon. So we're going to try water again just to see if our balloon was really properly charged. And as you can see, the stream of water is bending in the direction of the balloon, clearly indicating it's even going outside the cup and making a big mess. So clearly water is a polar molecule, therefore the molecule bends or get attracted to a charge, whereas non-polar molecules like xylene do not have any oppositely charged poles, and therefore they do not respond or do not get attracted to a static charge. All right, so the water molecules, they're strongly attracted to each other, and that's because they are polar molecules. So the positive pole of one molecule gets strongly attracted to the negative pole of the other molecule. As you can see, these are strongly attracted, and this attraction is also called as hydrogen bonding. So what happens is sometimes the attraction is so strong that this little tiny hydrogen atom gets so strongly pulled by this oxygen atom of the other molecule that it completely disassociates itself from its molecules by losing its electron. And then as it does that, it turns into hydrogen ion, whereas the remaining part of the molecule, which is made of only oxygen and hydrogen atom, is called as hydroxide ion. So since this ion has lost its electron, it has turned into a positive ion, and that's called as hydrogen ion. On the contrary, the other remaining part, a water molecule, has one extra electron because this electron is still being left with it, and this is called as hydroxide ion, O and H negative. So that's an hydroxide ion. So water disassociates into hydrogen and hydroxide ion. Now what happens is this hydrogen ion does not necessarily stay by itself. What happens is when the other water molecule was attracting it, right, it gets so much drawn that as soon as it disassociates, it goes and attaches itself with this other water molecule. Now, as you can see, this water molecule now has 3 hydrogens and 1 oxygen. So the formula of this molecule becomes H3O, and it also acquires a positive charge because of this positive hydrogen ion that has attached itself. So technically, hydrogen ions and the hydrogen ions and the hydroxide ions, they are one and the same thing. They are not very different. Simply when the hydrogen ions attaches itself to a water molecule, it becomes hydronium. So they are technically one and the same thing. So we're going to treat hydrogen and hydronium ions as one and the same thing. And so I want you to remember that these are same substances. All right. So what happens is if someone asks you to determine the concentration of these hydronium or hydrogen ions in pure water, if you want to determine that, you're going to realize that 1 out of 10 million water molecules are actually hydronium ions. So it's a very extremely small number of water molecules that change into hydronium ions. So 1 out of 10 million means 1 out of 10 raised to the power 7, right? And so if we were to express the concentration of hydronium ions, and the way the concentration is written in science is you write down the name of the substance and put a bracket around it. So that's how we write down the concentration. We don't have to write in full sentence like concentration of a substance. We simply have to write the name of the substance and put a bracket around it. So this means the concentration of hydronium ion, right? So if we were to write the concentration of hydronium ion, we're going to say it's 1 out of 10 raised to the power 7, right? And so the other way of writing it down is 1 times 10 raised to the power minus 7. And so you might be thinking, this looks so complicated to write down the concentrations, and it's so difficult to remember, right? So if we were to compare substances based on concentration of hydrogen ions, it's going to be so hard. So scientists, they came up with a very easy and simple method of expressing the concentration of hydrogen ions, and that's called as the pH. So we know so far pH is also called as power of hydrogen ions, and it is expressed as negative logarithm of hydrogen ions or negative logarithm of hydronium ions. As we said, they are one and the same thing, right? So if we were to find the pH of pure water, we're going to realize the pH of pure water is going to be negative log of 1 times 10 raised to the power minus 7. And that's going to give you the number 7. And let me tell you, please don't be intimidated by logarithms. They are very simple to work with as long as you know how to use a calculator. That's all you need. All right, what does pH 7 mean? pH 7 mean you have a same concentration or equal concentration of hydrogen and hydroxide ion. So the concentration of these two ions, when the concentration of these two ions is the same, then the substance has pH 7, which is also called as the neutral pH, and that's the midpoint on a pH scale. If the if the pH of a substance is greater than 7, what it means is that substance is going to have lower concentration of hydrogen ions and a higher concentration of hydroxide ions. So higher pH means lower hydrogen ion concentration, and those substances are called as bases. So bases are primarily hydrogen acceptor. They accept hydrogen. So what happens is if you dissolve a base in water, it's going to start gobbling up whatever hydrogen ions are present in water, and therefore the hydrogen ion concentration goes down. So those are bases. Now if the pH is less than 7, then what happens is the hydrogen ion concentration becomes more than hydroxide ion concentration. And what that means is when you dissolve any substance that's acidic in nature, what it does, it releases or it produces or donates hydrogen ion, right? So acids are substances which are called as hydrogen donors because they donate hydrogen ions, and as a result, the hydrogen ion concentration in acids is more than hydroxide ion concentration. So basically acids and bases are simply determined on the basis of balance between hydrogen and hydroxide ion concentration. And as you know, acids and bases can be very corrosive depending on their strength. So stronger the acid or stronger the base, more corrosive it is. Now we will learn how to make red cabbage pH indicator. For that, you need a red cabbage. You just need a small bit of red cabbage, and you need a pot that's halfway filled with water. Allow it to boil, let it heat so that it boils. What you need to do is you need to roughly chop red cabbage. Now, all this needs to be done under adult supervision. If for some reason you're not allowed to be around knives, then you can simply break this red cabbage and dump it into this pot. So I'll show you what the next step is going to be. Our pot is ready. It's hot. And so I am going to add all the red cabbage into the pot and then allow it to sit for at least 10 minutes. So that means this is going to simmer for 10 minutes and we'll be back after that. Okay, so we are back. This pot had been simmering for 10 minutes and then it was allowed to cool down for additional 15 minutes. Now we're going to go ahead and strain our cabbage to get the indicator. So if you notice, the cabbage looks blanched and pale. That's because it lost all its anthocyanin pigment. It is this pigment that's responsible for red color in cabbage. And what happens is as you boil, all this color is able to get dissolved in water and it seeps out from the cabbage and gets mixed with water. So that's what our pH indicator is. So the anthocyanin pigment is also present in blueberries, in plums and radish. So if you want to make a pH indicator from them, you can definitely do that. In fact, you can make a pH indicator and compare them for their efficacy. By the way, all this cabbage that we cooked, you don't need to throw it away. You can eat it. In fact, you can use it in your soups and consume it. All right, now I'm going to show you the experiment I did with eggs. So I had these eggs soaking in different beverages for 2 days now. The reason why I performed this experiment is because I wanted to see how these different beverages, they impact the surface of the egg, which is the eggshell. Now, eggshell is made of calcium carbonate, which is the same substance or the same compound that actually makes the shellfishes, the shells of shellfishes, and the corals. Even our teeth are made of compound of calcium, which is called as hydroxyapatite. I know it's kind of mouthful, but that's the name of the compound that our teeth are made of. So since our teeth, eggshells, and coral reefs, as well as the shells, they are made of compounds of calcium, our findings of this experiment can be easily applied to our teeth as well as to coral reefs and shellfishes. So that's the whole idea. All right, so what I did is I determined the pH of each of these solutions or these beverages. And this is how I determine the pH. I use my homemade red cabbage pH indicator. So what I did was I took a spoonful of each of these beverages in different cups, and then I added a little bit of my pH indicator, and I waited for color to develop, and I matched that color with the pH chart, and that allowed me to determine the pH. All right, so let's make our observations for each of these eggs. So first I'm going to observe the egg that's been soaking in distilled water, which is pure water. All right, so when I take out this egg, as you can see, I don't see any visible damage. I don't see any stain. I don't see anything peeling off. So it looks like fresh and new to me. And if I check the pH of water, I already determined the pH is approximately 7. It's very close to 7. All right, so let's move on to the next beverage. The next beverage that I used was orange juice. And again, as soon as I look at my egg, I hope you can see it. It looks more whitish in color, and that's primarily, as I try to gently scrape off the surface with my thumb, I can see the top layer peeling off and the white portion being exposed. So clearly there's a lot of corrosion going on here, and and even the top layer is peeling off. And when I checked the pH of orange juice, the pH was close to 3. So it makes sense because orange juice is highly acidic, and it definitely is way more corrosive. All right, the next beverage that I'm going to check is coffee. So this egg has been soaking in coffee for, again, 2 days. And as soon as I look at this egg, it seems to be deeply stained, but if I try to scrape off the stain, somehow try to get it off, I cannot, right? So it seems to have deeply percolated. So that makes sense. So coffee really could be staining a teeth much easily, right? And when I try to look at the pH of coffee, I notice, let me see, what is the pH for coffee? All right, the pH is close to 5. All right, so that's for coffee. Again, at times it's very difficult to determine the pH of coffee, and simply because it has its own color. But if you try looking carefully, then you should be able to see the shade. And if you match that shade, that's going to give you the pH. Next, I'm going to make my observations for the egg that's been soaking in soda. All right, as soon as I pick up this egg, I can definitely see the surface being stained, just like in coffee. But if I try to get the stain off, I'm able to do that. And it exposes the surface, the underlying surface of the egg. So I'm able to get the stain off, not all throughout, but in certain places. So clearly the stain doesn't seem to have percolated deep enough, and the damage is not as much for some reason, which is strange. All right, so next that I'm going to observe is the egg that's being soaking in the energy drink. Again, the pH for soda was 3, and the pH for energy drink is close to 2. All right, so when I look at this egg, I see a considerable damage already, just like in orange juice. And if I try to gently scrape off the top layer, I can see it coming off, and I can see the white layer, underlying white layer being exposed. So clearly there is considerable damage. So as you can see, the top layer, like I can easily scrape it off. So clearly it's being corroded by acidic drink or acidic energy drink. All right, next I'm going to make an observation for milk. So I determined the pH of milk, and this is like a purple color, and
the pH is close to 7. All right, I see the egg looks a little more whitish, and that's probably because of the milk that's making a layer on top of it. If I try to scrape it off, I can remove the layer of milk that has formed on it, and then I can easily see the shell of the shell more clearly. Now, if I look carefully, I don't see any visible damage. I don't see any staining, and I don't see any peeling off. So it looks like fresh to me, just like the egg that was sitting in distilled water. So clearly, I could see how different beverages, they damage the eggshell differently, and that kind of depends on the pH, So I summarize my findings in the chart that you see on the screen, and I would really encourage you to always summarize your findings either in the form of a table or a chart or a graph, because that allows us to see the trend. If I were to arrange these beverages from most damaging to least damaging, I will put energy drink first, followed by orange juice, followed by soda, because soda, the surface was stained and I could remove the stain, and I could see an underlying layer being exposed. Coffee, it was simply stained. I could not see any visible damage. And then water and milk, I will put them together. They were not damaging at all. So milk is not only good for your teeth because it does not cause any damage to your teeth, but it's also good for your teeth because it gives you that calcium that your teeth needs. So again, we want to go back to the fact that corals and shellfishes, they are on the verge of extinction, because do you know that the oceans, they have become 25% more acidic since pre-industrial time? And as you can see on the picture that's being shown on the screen, you can see the acidity with the change. You can see the change in color, and that represents the acidity of the ocean that has changed over time. And so clearly, if we don't do something about it now, then there's a possibility that corals and shellfishes, they become extinct in coming years. So similarly, acidic environment is clearly very harmful to our teeth, right? And to make matters worse, if we have food particles sitting in or sticking to our teeth, then what happens is the bacteria starts acting on it and ferments them and produces more acid that corrodes the teeth even more. So clearly, we have to be very mindful of what beverage we choose to drink. There is no escape from brushing your teeth twice a day, right? I want you to perform these experiments with eggshells, and you don't have to really use whole eggs. You can simply use eggshells, so that ways you don't end up wasting eggs, right? And you can use any beverage that you normally drink, or you prefer to drink, or you want to try out, and determine whether this beverage is good for your dental health. And I would like you to share your findings and share your experiments so that we can learn about your findings. And do reach out to us if you have any questions.
So I did the same experiment that Miss Chirulu did, except I left these eggs for 7 days. We're gonna see what they look like after a week in soaking in all of these different liquids. We have water, orange juice, coffee, Diet Cola, energy drink, and milk. So let's see what that effect of the different pHs of these, so how much acid or not there is in these, what the effect of those is on these eggs. Now, remember, these eggs are the eggshells are made of a substance called calcium carbonate. Calcium carbonate is really similar to what your teeth enamel is made of. So a really good thing to think about while we're looking at these eggs is how do these different drinks, what effect do they have on our own teeth and our own teeth health? Let's take a look at water. Water has a pH of 7, which, as you can remember, is neutral. So what do you guys think? will it have an effect on this eggshell? If I take a look at it, I don't see any difference. So I'm going to give it a brush with a toothbrush, just like you would with your teeth. Let's see if it does anything. Nope, I don't see any of that eggshell, any physical change to that eggshell happening. This eggshell is in perfect health, just like it was when we put it in there a week ago. Interesting. Let's take a look at orange juice. Now, we hear orange juice is healthy, it's good for you, it's made of fruit, it's got vitamins. Some of those things are true. Now, orange juice in moderation can be good for your health, but imagine if your teeth were exposed to it constantly. Let's see what effect it would have. Orange juice has a pH of around 3.8, which is on the acid end of our pH scale. Whoa. Okay. Now, I'm gonna let you guys take a look at that. This was not orange juice with pulp, so that is not OJ that you are seeing on there. That is likely some of that eggshell. Oh, get a good handle on it. Let's take a look and see if we can brush any of that eggshell off. Oh yeah, I'm getting definitely some chunks here. We are seeing a reaction. This eggshell reacted to the acid in the orange juice. It did eat away at some of that shell. That's pretty gross. I'll leave that there. So we went from a neutral pH to an acid here. Our next one is coffee. What do you guys know about coffee? Yep, it stains your teeth. So before I even pull this egg out, you can probably predict that the egg will not be white. As a coffee drinker myself, I know that does happen to your teeth. So let's see. Yep, coffee teeth, coffee egg. Take a look at that egg, it's brown, and that is directly from that coffee. Coffee has a pH of around 5, so less acidic than our orange juice, more acidic than water. So can you make a prediction based on that? Let's see, if we brush it, will our eggshell have experienced any change? Give it a good brush. I'm not seeing a lot of effects on that shell itself. Still pretty hard, but I am able to brush off some of that color. Okay, so we do see some of the staining effects of coffee. Not too many changes to the health of that eggshell. All right, let's put our coffee down. Our next one is Diet Cola. Now, Diet Cola is pretty acidic. Maybe you've done an experiment in the past where you were challenged to clean a dirty penny with cola, and that works because of the acidity of Diet Coke. Diet Cola has an acidity of around 3, which is more acidic than orange juice can be. So we should see a greater effect on the health of that eggshell. And again, that's why if you've ever done that experiment with the penny, that's why you are able to clean the penny off, because it's so corrosive. Let's take a look. Whoa, that is gnarly. Let me show you that nice and close. What you're seeing there is not old Diet Coke dried up on it. That is actually eggshell. That is eggshell that has reacted with the acid in that Diet Coke. And I can brush it off. And what you're seeing brushed around is bits of that eggshell that are no longer where they were a week ago. It's pretty gross, pretty gross. All right, we have 2 more left, and we have our energy drink and our milk. Now the energy drink, you guys like them because they're sweet, they're sour, they get you all hyped up, but they can have really damaging effects on your teeth. Before I even take it out, can you see what I see? I don't know if you can see that, but I'm looking at this eggshell, and it does not look like an eggshell anymore. It almost looks like coral in a coral reef or something. It's grown out of the egg. That's disgusting. Let's take a look. Whoa. Wow, take a look at that. What you're looking at is not energy drink that's started to just build something. This is actually that calcium carbonate from that egg. It's been reacting and corroding this whole time for a week. I'm touching it and it feels like it's almost covered in sugar. It's broken off so much. And right here, you're seeing some buildup. This is the energy drink eating away at this egg. Now imagine again that this egg is your teeth. This is what could be happening if you're not brushing your teeth or at least rinsing your mouth after you're drinking these very, very acidic things. Let's give it a brush because that's the best part. Let's see if we can brush this away. Oh, ew, yuck. I am brushing away layers of that eggshell. You wouldn't want that happening to your teeth, would you? All right, our last one is our milk. We all know milk is good for your bones, good for your health, makes you strong. We're told that all our life. And one of the reasons why it's good for you is not just all the vitamins in it, but it is pretty neutral. It's going to have a very similar pH to water. So can you make a prediction? What would that be like on our egg? If it has a similar pH to water, what could you expect? Well, I would predict that we're not going to see too much change at all. That it's going to be very similar to our egg that we took out of the water. And sure enough, I don't see much difference in this egg whatsoever. I'm going to give it a brush. See if any eggshell comes off. I still have some bits from the last one on there, but on this eggshell, I don't see anything coming off of it. This eggshell is still in peak condition. So, all of these drinks, different acidities, different effects on the health of this eggshell. You can always, again, think of that as your teeth. So, if you're drinking these highly acidic beverages, best thing you can do is at least rinse your mouth with water when you're done, but always, always, always brush your teeth twice a day to prevent this from happening. Yuck! For our next experiment, I'm going to show you how you can make your very own rock candy in your own home. For this experiment, you'll need scissors, sugar, either string and a pencil or wooden skewers, a measuring cup, a jar or a cup, and some food coloring. That part's optional. You'll also need something to cook in, and if you're too young to use the stove, an adult to help you. The day before you're going to make your rock candy, either take your string or your skewer and get it wet and roll it in some sugar. These are going to be the seeds to your crystallization. We'll talk more about what that means later, but it is very important that this is dry before you dip it into the solution you're going to make. So give it about 1 day to dry before you put your experiment together. I'm going to show you how to make your rock candy now. First, you need to start with 1 cup of water. Get that water boiling nice and hot. 1 cup of water is all you're going to need, but you're going to have to start with at least 2 cups of sugar. Start pouring this in slowly, not all at once, and giving it a good stir. As soon as the sugar dissolves, add some more to it. Your water should start to look pretty syrupy, but you can still dissolve sugar. In fact, you can dissolve more than 2 cups of sugar, and you're going to need to. At this point, start adding sugar until you just can't dissolve any more of it in the water. You can add it a little bit at a time, or you can add about a whole cup at once if you're in a rush. In the end, we'll take about 3 cups of sugar for 1 cup of water. You'll reach a point where the water cannot hold any more sugar in it, and that's when you know that you'll have saturated your solution. A little bit more. It's very important that you get as much sugar as possible in that water. Otherwise, you may have to do your experiment again after a few days if you don't notice any growth. So I think we're there. Go ahead and turn your heat off. And at this point, go ahead and add a little bit of coloring to it. I'm gonna add a couple drops of green here. Mix it up. and then take it off of your stove and let it sit for about 20 minutes. Now, once your solution's cooled for about 20 minutes, you're gonna notice it's very, very syrupy. I have one here that's already nice and cool. Before you dip your string or your skewer into it to start growing your crystals, go ahead and pre-measure it. So what I did is I tied my sugar-soaked string on here, the one that I let dry overnight, and I tied it to a pencil, and I cut the bottom off so that we have about half an inch at the bottom of the cup. That way you don't grow crystals from the bottom of your glass, you grow them only on your string or your skewer. Once you have that proper length, you're going to go ahead and dip it into your solution, your cooled off solution. Once you do this, do not touch it again for several days. After you've let your solution sit for a couple of days, you should really start to see some growth on your string or your stick. Here's what mine looked like after about 3 or 4 days. This is the one on a stick, but I also did one on a string, so if that's what you're doing, let's take a look at the one I have on a string. Pull it out of there, dry it off a little bit. Ooh, that looks like a treat. Take a look. And again, this is just after a couple of days. So if you gave it more, say 7 or 8 days, you could have rock candy that looks like the kind you could buy in a store, all made at home and due to some science. So let's talk about that science. Remember, I asked you to make sure that your string or your stick was rolled in some sugar and dried before you stuck it into your solution. There's a reason for that. When we heated up our water, we were able to put some more sugar in it than normal. Think of like if you've ever tried to sweeten some iced tea. If it's cold, you can only stir so much sugar into it before it starts to sink to the bottom, right? But if you have hot tea, you can actually add more sugar to it than iced tea. And that's because the amount that we can saturate that water with increases as the temperature increases. Let's talk about the word saturation. When you saturate something in a solution in chemistry or science, we're saying that we're adding as much as possible of a certain substance into the other one as it can hold. Think of it like a sponge. If I have a sponge and I'm filling it with water, there's only so much water I can put into that sponge before it starts to drip out, right? So I've saturated that sponge. There's 1 drop of water that's too much for it. Now, as far as this goes, there's only a certain amount of sugar that cold water can hold. But if we heat that water up, we can add more sugar to it. You saw us add about 3 cups of sugar to 1 cup of water. You couldn't do that if that water was room temperature or cold. Now, when it cooled down, what happened was all that sugar that was dissolved in your hot water was still in there, but now it was very, very unstable. It doesn't want to stay in there the way it is. So that's why we put the string in there. So the string actually, or your stick, gave all that extra sugar somewhere to go. See, every little piece of sugar, every little sugar molecule that you had that dried onto that string was what we call a seed or a nucleation site. Nucleation sites or seeds kind of help that crystallization start. It gives all that extra sugar somewhere to go. All that extra dissolved sugar is just floating around in your solution and it doesn't want to be there. It's unstable. So when we give it something to latch onto or glob onto, think of being in a really crowded room and then all of a sudden having somewhere new to go. It's going to do that. So over time, all that extra sugar starts building up, and because of the molecular structure of sugar, we see this beautiful crystallization starting to occur on our rock candy. And the longer you leave it, the more sugar is going to build up and build up and build up on there until your solutions reached the normal saturation amount that would be at this temperature. Now, I bet you're wondering why the Mentos and Diet Coke is on the table. And the reason is these two experiments are very, very similar. They have very similar causes and effects of what we see happening. we put the Mentos in the Diet Coke, we saw a huge effect. We saw an explosion, right, of all of that liquid that was in there going up very far. Now, what does a little Mentos have to do with that? We look at these and they seem kind of smooth, kind of plain, but it has everything to do with the surface of this Mentos. Mentos? I don't know, Mento. If we put this under a microscope, it would actually be super, super bumpy. It would look a lot like gravel, concrete. It would actually look a lot like that sugary stick or sugary string that you did in this experiment. And all those bumps, those nooks and crannies, are nucleation sites, are seeds for growth of something. What is that something though? Inside of your Diet Coke, we have a whole bunch of carbon dioxide gas. That's what gives it that good fizziness. And normally that carbon dioxide gas in this solution is trapped in there. It's trapped in there by the pressure that holds it in there in the bottle. Now, we could easily get it out by letting this just go flat over the course of a week or so, right? But we can get those bubbles out really, really fast by giving them somewhere to go. When you drop that Mentos into your Diet Coke, you're giving all those carbon dioxide bubbles in here that are saturated, super saturated in this solution, somewhere to go. And they jump onto those little nooks and crannies, and they jump onto each other, one after another, but it happens so fast that all that carbon dioxide, as much of it as possible, comes out of that solution. So just like your rock candy, your Mentos is giving something somewhere to start building, a nucleation site, a seed for growth. In this case, it's just carbon dioxide. These are both experiments you can try at home. I'll tell you one thing, this one always works. This one, you might have some troubleshooting to do with it. Mine didn't work the first time, and I had to look up ways to fix it, and I had to figure out why it wasn't working. And I recommend that you do the same. Feel free to contact me. You'll see my information on the slide coming up if you have any questions, if you want me to help you figure it out, or if you just want to show off your own experiment. I would love to see it. Hopefully you guys had a good time, learned something, and good luck trying these experiments at home.